During the past several years, this nation has worked toward an operational capability for manned space exploration. Providing a focal point and timetable is the Apollo program, in which manned exploration of the moon will begin within this decade. Manned spaceflight began in the Mercury program. Emphasis shifted next to filling hardware pipelines and then to development testing of major space vehicle systems for the Gemini and Apollo programs. During the past year, emphasis shifted to the next phase, the qualification of the hardware and the development of the operational techniques necessary for a broad-based capability for manned spaceflight. The Gemini program, which entered its manned flight phase early in 1965, is a keystone in the nation's development of an operational capability for manned space missions. The Gemini spacecraft is built by McDonnell Aircraft, St. Louis, Missouri, and the launch vehicle is built by the Martin Company, Baltimore, Maryland, under an Air Force contract. In the 5 manned Gemini flights, 2 more than originally scheduled in 1965, efforts were concentrated on the qualification of concepts and procedures for space operations and on the medical qualification of man for the lunar and other extended space missions. This is separation of the first stage, photographed by a tracking camera on the ground. During the missions, which included 4, 8, and 14-day flights, it was shown that valuable scientific work, such as Earth terrain and weather photography, could be performed. Crew training procedures were shown to be sound, as evidenced by astronaut performances in long-duration flights. It was proven that a man outside his spacecraft could, without disorientation, control himself with either a maneuvering unit or a tether, and further that he could do useful work. Operational flexibility was increased, as illustrated by the December flights of Gemini 7 and Gemini 6. The decision to attempt the dual flight mission was made after the original Gemini 6 mission was canceled because its Agena target vehicle failed to achieve orbit after launch. Gemini 7 was launched from Cape Kennedy, Florida, Complex 19, on December 4th. And following second stage cutoff and separation, the crew began 14 days in orbit. Immediately after the Gemini 7 launch, Gemini 6 was erected on the same pad, and despite problems, the vehicle was launched on December 15th, only 11 days after Gemini 7, and well within time and trajectory constraints required for planned rendezvous maneuvers. As the mission progressed, the Houston Mission Control Center, built by Philco and activated in the spring of 1965, was proven capable of directing 2 flights simultaneously, a capability made possible by the Worldwide Tracking Network under the direction of NASA's Office of Tracking and Data Acquisition. The network is manned by an international team of personnel. Network information is relayed to the NASA Goddard Space Flight Center, then relayed to the Mission Control Center in real time. Supported by the Control Center and Tracking Network, Gemini 7 and 6 achieved rendezvous after a series of complex orbital altitude and plane changes by Gemini 6. The Gemini 7 crew was alert and capable even after 11 days in space. The 2 spacecraft closed within 1 foot. With such maneuvers vital to future space operations, upcoming Gemini missions will be devoted not only to rendezvous, but to docking with the target vehicle as well. It was also proven in the Gemini 7 flight that man can live and work in space for 14 days, a period longer than all previous American flights combined and almost twice as long as the Apollo lunar mission. In addition, progress was made during the year in controlling re-entries, as contrasted with the Mercury spacecraft, which re-entered in a ballistic trajectory. Re-entry here is illustrated by footage from an early Gemini flight. Both Gemini 7 and 6 landed within less than 10 miles of planned impact points, and as in all previous manned missions, were picked up by Navy recovery units. In the past year, significant program objectives were achieved in Gemini, building confidence that man can adapt to space and weightlessness, and that Apollo objectives will be met as well. In the present year's Gemini missions, operational proficiency will be increased still further. Another keystone in the development of an operational capability was Saturn I, which completed its flight program on July 30th, 1965. Saturn I, with its unprecedented 10 successes in 10 programmed flights, qualified design, manufacturing, testing, and operational concepts, and qualified systems, subsystems, components, and parts essential to the development of the launch vehicles for the manned Apollo missions. Unlike earlier programs, intense emphasis was placed on detailed ground testing to the point that flights were considered to be qualification rather than development of hardware. Procedures were established for using large volumes of super-cold fuels. New guidance and instrumentation equipment was developed and will be used for the more advanced Saturn vehicles. Sensing and valving equipment for propulsion systems was perfected to ensure full propellant usage even in the event of an engine-out condition. Here, first-stage propellant behavior is illustrated by onboard camera footage photographed during a mission. The state-of-the-art of liquid-fueled engines was further developed, helping pioneer the operational use of liquid hydrogen engines. In this sequence, the separation of the first stage and the ignition and burning of the liquid hydrogen engines were photographed by an onboard camera. Further, Saturn I placed Apollo test spacecraft into Earth orbit for the first time and launched Pegasus meteoroid detection satellites into near-Earth orbit. Data from the Pegasus, developed under direction of NASA's Office of Advanced Research and Technology, has helped verify structural design of the Apollo spacecraft. The overall success of Saturn I is illustrated by the fact that it reached operational status in its 6th instead of 10th mission as originally planned. Saturn I helped prepare the way for Apollo with an uprated Saturn I, scheduled for its first launch in early 1966 from the John F. Kennedy Space Center's Complex 34. The unmanned suborbital mission will be of major significance. The Apollo uprated Saturn I, vehicle for the initial Earth orbital manned Apollo missions, will be launched with all systems up in its maiden flight, thus setting a pattern for the development of future manned space vehicles. The spacecraft will be the first equipped with Apollo flight systems, and the uprated Saturn I will be equipped with a new second stage and instrument unit. Major objectives are to demonstrate the operational capability of the spacecraft launch vehicle combination and to fire the spacecraft propulsion stage in space. Objectives also include an evaluation of mission support facilities. Launch Complex 34, since its use in the first Saturn I, has undergone considerable modification to provide automatic checkout and launch. To ensure mission readiness, the Apollo uprated Saturn I has undergone extensive ground qualification testing. For example, at North American Aviation, Downey, California, a water drop test of the command module, shown here from an underwater camera, verified structural reinforcing of the aft heat shield under the most severe impact conditions anticipated for the mission. This marks the correction of an earlier design problem. In a series of static test firings at the White Sands Test Facility in New Mexico, the spacecraft propulsion system was qualified for flight on the mission. The Communications and Data System, built by Collins Radio, Cedar Rapids, Iowa, was qualified, as were the Spacecraft Propulsion Module Reaction Control System, built by Marquardt in Van Nuys, California. The Stabilization and Control System, built by Honeywell in Minneapolis, Minnesota. And the Command Module's Reaction and Control System engines, built by Rocketdyne. And at the Army's White Sands Missile Range, the Apollo Launch Escape System attained flight qualification, completing a series of pad and launch abort tests. Launch vehicle work, too, was characterized by extensive ground qualification testing. At the Michoud plant near New Orleans, Chrysler completed structural qualification tests for major assemblies of the uprated Saturn I first stage. At Huntsville, Alabama, contractor personnel performed instrument unit vibration tests, a part of the unit's electrical and mechanical qualification. The testing of major units was paralleled by qualification of small parts. For example, guidance system components manufactured by IBM, liquid oxygen tank pressurization control modules developed by Air Research, Phoenix, Arizona, and first stage fins tested by Chrysler at Michoud. In addition, the Marshall Space Flight Center completed dynamics testing for the entire Apollo uprated Saturn I vehicle. The successful launch of the first Apollo uprated Saturn I will be a major step toward qualifying the vehicle for manned missions. Spacecraft and launch vehicles for upcoming missions, even the first manned flights, were already well along in manufacturing and pre-flight checkout. The past year was marked by many accomplishments in the preparations for Apollo uprated Saturn I flight operations. It was also marked by accomplishments in development and qualification work for Apollo Saturn V, the vehicle for the manned lunar mission and other operational capabilities. While ground test spacecraft modules designed for the lunar mission were being manufactured, development and qualification work was in progress for subsystems. The liquid hydrogen, liquid oxygen fuel cell, developed by Pratt & Whitney, East Hartford, Connecticut. Guidance and navigation equipment, manufactured by AC Electronics, Milwaukee, Wisconsin. Lunar module ascent and descent engines built by Bell Aerosystems and TRW at Buffalo, New York, and Redondo Beach, California. And the lunar module landing system, built by Grumman Aircraft. At the Manned Spacecraft Center, 3 different prototype Apollo spacesuit assemblies, developed by 3 different contractors, were evaluated and compared in a comprehensive testing effort. After each prototype was tested under identical conditions, the suit assembly developed by International Latex, Dover, Delaware, was selected. Meanwhile, in the development of Saturn V, ground testing similar to that conducted for Saturn I and the uprated Saturn I was in progress with the same attention to detail. Being tested, for instance, were first-stage umbilical plugs at Boeing, engine activation system components at North American, and the second-stage separation system at North American. And while all engines were attaining qualification for manned flights, Saturn V's 3 stages underwent their first series of full-thrust, full-duration static firings. Full thrust for the first stage, shown here, is 7.5 million pounds. It uses liquid oxygen kerosene propellant. The 5 engine firings of the Saturn V second stage, which is powered by liquid hydrogen, liquid oxygen, were a significant step forward in propellant technology. Liquid hydrogen, liquid oxygen propellants power all Saturn upper stages and provide 40% more thrust per pound than conventional propellants. Structural and dynamics testing was also in progress. At Marshall, for example, several major assemblies of the first stage, being developed by Boeing, had been structurally tested. In a Douglas Aircraft California facility, structural testing of the third stage, which burns liquid hydrogen, liquid oxygen, was essentially complete. At North American, structural testing of the second stage was completed. However, at peak design overloading, the stage ruptured. Loss of the stage interrupted dynamics testing, but another development stage already in existence will be refitted and used for the completion of dynamics testing. Meanwhile, at Marshall, dynamics testing proceeded for the vehicle's third stage, instrument unit, and spacecraft. While Apollo and Saturn V spacecraft and launch vehicle systems were being qualified for manned missions, manufacturing of flight hardware moved steadily forward throughout the year. By the end of the year, both command and propulsion modules were in manufacturing at North American. For example, the command module for the first Apollo Saturn V flight, an unmanned mission, was undergoing heat shield fit checks. In addition, the first flight lunar module, which will be launched in an unmanned uprated Saturn I mission, was in structural assembly at Grumman Aircraft, Bethpage, New York. The first stage for the first Saturn V flight was undergoing tests for static firing at Marshall. In the tests, automated Saturn V checkout equipment was used for the first time. Major assembly continued at North American and Douglas for the second and third stages, scheduled for the first Saturn V flight. And IBM began assembling the first several instrument units. Like flight hardware, ground support facilities are essential for men to operate in space. During the year, one of the Manned Spacecraft Center's major environmental chambers became qualified for manned tests of spacecraft in simulated space conditions. Despite considerable damage from Hurricane Betsy, the Boeing Michoud Test and Checkout Building was activated on schedule and used in post-manufacturing work. The Mississippi Test Facility was transformed from a site of earth and concrete work to a site of preparation for testing activities. Early in 1966, a Saturn V ground test second stage is scheduled for static firing in the first stand to be completed. Once finished, the Mississippi Test Facility will be used primarily for pre-flight checkouts of the first two stages of Saturn V. The John F. Kennedy Space Center's industrial area continued to build toward operational missions with, for example, construction being completed for two large-scale environmental chambers. These will be used in pre-flight checkout of Apollo spacecraft. The Central Instrumentation Facility was essentially complete. It will be used to monitor, analyze, and store information from launches and pre-flight tests. And at the Apollo Saturn V launch complex, which will provide for automatic pre-flight checkout and launching, the vehicle assembly building was converted from a 525-foot steel framework to a near-complete building. Inside both the high and low bay areas, work platforms and equipment were being installed. In the Launch Control Center, console racks were installed. Launch Pad A, with 8,000 tons of reinforcement steel and 114,000 cubic yards of concrete, was essentially finished, and Launch Pad B was well into construction. 3 umbilical towers were complete, and the first mobile servicing structure was topped out. The first transporter had undergone mobility and lifting tests. Modifications to correct a problem with one of the large bearings were completed, and the transporter was used to move an umbilical tower into the vehicle assembly building. As the nation approaches an operational capability for manned space exploration in Apollo, planners are looking ahead to determine how best to capitalize on the capability. And in meetings such as the Lunar Exploration Summer Conference held in Falmouth, Massachusetts, the advice of the nation's leading government, industrial, and university scientists is being sought. This meeting was conducted by NASA's Office of Space Sciences and Applications in cooperation with the Office of Manned Spaceflight. During the past year, emphasis was focused on the qualification of the techniques and hardware necessary for man to operate in space. And in spite of problems, considerable progress was made. In the present year, emphasis will shift further toward operations in flight, both Gemini rendezvous and docking missions, and Apollo uprated Saturn I missions. With increasing confidence that manned spaceflight goals will be met, the nation approaches still nearer to achieving the manned lunar mission within this decade, and thus establishing a broad-based ability for manned space operations.